Okay, hi, I am Rakesh and Kumar, and these are my team members, Shilman Danish, Tan, and Siti Aisha. Okay, I'll be talking about the introduction. And so for the introduction, I have 4 points, which is the first one is strategic importance. So methanol is a very vital platform chemical and clean fuel feedstock. And the second one would be the modern paradigm, transitioning from traditional fossil fuels to low carbon pathway by combining them with sustainable hydrogen systems. And third one will be chemical reaction, product produced via the catalytic hydrogenation of gases over specialized copper-based catalysts at high temperature and pressures. Downstream processing will be the fourth point. Because the reaction is highly exothermic and equilibrium limited, the resulting crude stream contains unreacted gases, water, and impurities that require robust purification.
Hi, my name is Siti Aisha, and in this part I'm going to explain about design of separator system. As you can see at the first column is the PFD, which is profile diagram based on symmetry, and the thermodynamic model is advanced Peng-Robinson's. Followed by the second column contain assumption and formula that can be used to obtain concentration. So the assumption is all gases behave as an ideal gas. The second one is value for universal gas constant, or also known as R, is 8.314. The formula might needed is first PV equals to nRT, Pi equals to YIP, and lastly Ci equals to N over V, also equals to Pi over RT. As you can see at the third column and the table, I attach the component that have in the separator system, followed by mole fraction and also concentration. How to obtain the concentration is by subs the value of mole fraction and pressure, temperature, and also universal gas constant in formula Ci equals to Pi over RT. Next is absorption purification system with 99.5% efficiency. At the first box, as you can see here, is the proposed purification stream, and the image attached here is based on the PFD at the previous slide. The second box is about how to achieve 99.5% efficiency for methanol, which is the first one is the multi-stage purification strategy was implemented or applied, and also the crude methanol stream leaving the reactor system contains various impurities including water, hydrogen, carbon dioxide, methane, and others unreacted gas. At the third spot is about purification strategy, which is consisting 3 stages. The first stage is about separation column, which is the reactor effluent first enters a separation column where gravity separates liquid water from unreacted gases based on density differences. This step removes most of the water and reduces impurities, preparing the methanol-rich stream for further purification. Next stage is adsorption column. The methanol-rich stream then passes through an adsorption column containing zeolite adsorbents, which selectively remove residual water and trace gases. This process increases the methanol purity to the required 99.5% while minimizing energy consumption compared to thermal distillation. And last stage is regeneration with pressure swing adsorption, or PSA. In this column is about a twin pad pressure swing adsorption system regenerates the zeolite adsorbents by lowering the pressure to release trapped impurities while the other bed remains in operation. This energy efficient approach enables continuous purification and maintains high methanol product quality.
In section 2.4, we examine our adsorbent selection and key process condition. We selected molecular sieve 3A or zeolite 3A primarily based on size exclusion. Water has a kinetic diameter of 2.65 Armstrongs, while methanol is larger at 3.8 Armstrongs. Because zeolite 3A has a pore opening of exactly 3.0 Armstrong, water is selectively absorbed into pores while methanol is completely excluded. We chose Zolite 3A over common alternative like silica gel or activated alumina because they are larger pore size above 20 Armstrong, cause significant methanol to co-absorption. Similarly, biochar and activated carbon lack the required polarity, resulting in poor working capacity. For operating conditions, we maintain temperature at 25 to 35 degrees C to favor exothermic fi- physio-absorption and maximize water uptake. The system pressure is set at 19.5 bar to match the upstream flash separator, preventing pressure to drops and keeping the stream in the liquid phase. Using a bulk density of 700 to 750 kg per meter cubic, we established a design equilibrium capacity of 0.18 kg of water per kilogram of adsorbent. Next, moving to section 2.5, we calculate the total absorbent mass required per bed. Our feed stream AU1L0 enters at 98,847.86 kg per hour total liquid flow, consisting of 66,501.76 kg per hour of water, 32 32,346.10 kilogram per hour of methanol, and trace of carbon dioxide (CO2). To achieve our product purity target of 99.5 weight percentage methanol, allowable water at outlet is capped at 162.54 kilogram per hour. Subtracting this from the feed give a required water removal rate of 66,339.22 kilogram per hour. Based on the Langmuir isotherm, we use our conservative design equilibrium capacity of 0.18 kg of water per kilogram of adsorbent. For an 8-hour operating cycle per bed, total water absorbed is roughly 530,714 kg. Dividing this by our equilibrium capacity, give a theoretical absorbent mass of 2.59 million kg, applying 1.25 safety factor for bed degradation and flow distribution. Our final design requirement comes out to 3,685.5 tons of molecular sieve 3A per bed. Next, I pass it to my friends.
Hi, I'm Jai. I will be explaining about continuous absorption column design. In our project, a fixed bed absorption column is selected due to its simple design, high separation efficiency, and column industrial applications. Before entering the absorption column, the reactor effluent is first cooled. The stream then flows downwards through a packed bed of Geolite 3A molecular sieve. Inside the column, water molecules are selectively absorbed between the pores of geolite, while methanol passes through due to the molecular sieve's pore size selectivity. The downflow configurations helps to improve flow distributions, enhance contact between the fluid and absorbent, and reduce channeling. To achieve continuous separations, a dual-column thermal swing adsorption system is proposed. During operations, one column functions as the absorption bed to remove water from methanol, while the second column undergoes regeneration through heating to remove the adsorbed moisture. Once the active bed reaches saturation or breakthrough, the feed is switched to the regenerated bed, allowing continuous purifications without interrupting productions. Next, I will be presenting the calculations. By using the absorbent mass calculated before by my teammates, we divide it by 2 to achieve the absorbent mass required by each column, which is 1,841.65 tons. To calculate the bed volume, we use the bulk density of 700 kg per meter cube, mentioned by my teammate before. We can get the bed volume is 2,632.5 meter cube. By assuming the height is 4 meter, we can get the diameter required is 28.96 meter. To summarize it, the preliminary column design consists of a fixed bed column with a diameter of 28.96 meter, a height of 4 meter, and a total bed volume of 2,632.5 meter cubed. The absorbent selected is Zeolite 3A due to its high selectivity for water removal. During operations, water absorption occurs progressively along the bed, performing a mass transfer zone. When breakthrough occurs, the saturated bed is regenerated to restore the absorption capacity and prepare it for the next cycle. Next, I will explain the operating conditions selected for the absorption column and the TSA regeneration strategy. The operating conditions are chosen to maximize water removal while keeping methanol in the liquid phase. The absorption temperature is set at 60 degrees Celsius because lower temperature generally improves absorption efficiency. The pressure is maintained at 7,500 kPa to ensure methanol remains in the liquid phase and to support integrations with the upstream process. A bed porosity of 0.4 is assumed, which is a typical value for pack absorption bed. The absorption capacity is set as 0.2 kg water per kg absorbent, representing a typical value for Geolac 3A used in dehydration applications. A downflow configuration is selected to reduce channeling and improve contact between the methanol stream and the absorbent. This figure illustrates the adsorption cycle for methanol purifications. During the adsorptions, water is removed from the methanol by the adsorbent. The adsorbent is then heated to regenerate it, allowing the adsorbed water to be released during desorptions. Finally, the column is cooled and made ready for the next adsorption cycle. For regenerations, a temperature swing adsorption (TSA) method is applied because water molecules are strongly retained in the micropores of Geolite 3A. During regenerations, the saturated bed is isolated and heated using hot purge gas to around 180 to 250 degrees Celsius. This increases the mobility of water molecules, allowing them to be dissolved and removed from the absorbent. After the regenerations, the bed is cooled before returning to absorption operations. The cycle times down are conceptual estimates to demonstrate the TSA strategy. The TSA cycle consists of three main stages. The absorption stage takes approximately 8 hours, where water is removed from the crude methanol. The regeneration stage takes around 3 hours for thermal desorption, followed by a 1-hour cooling stage to restore desorption capacity. Overall, these operating conditions allow continuous methanol purifications by improving water removal efficiency, maximizing absorbent performance, and reducing downtime during operations.
So for the conclusion, there are 3 points. Integrated conceptual design successfully developed a technically viable, efficient and low carbon methanol plant by linking sustainable CO2 hydrogenation with advanced downstream purification. Second one is reactor optimization. Determine the ideal temperature, pressure and catalytic settings to maximize carbon conversion and methanol selectivity, overcoming the equilibrium limitations. Lastly is high purity purification. Design the continuous solid adsorption system with an active regeneration energy strategy, successfully purifying the crude system to meet the strict industrial standard of 99.5% pure methanol.